Hello everyone, my name is Ramtin and here I want to talk about reconstructing phylogenetic trees in parallel from queries. So phylogenetic trees represent evolutionary relationships among a group of objects. For example, biological entities and such as species, bacteria or viruses, and each biological phylogenetic trees represents evolutionary process of these biological entities. And on the other hand, in the digital phylogenetic tree, each node represents a data object such as a computer virus, a text file, or a document, or a multimedia object such as an image or a video. And the relationships show how these objects have been edited, or have been compressed or corrupted. So the problem here is that we are given a set of leaves or nodes of the phylogenetic tree, and the goal is to find the set of edges of the tree using queries. And the queries may involve leaves or any nodes of the tree depending on the context of the problem. For example, on the left-hand side, we are querying leaves. On the other hand, on the right-hand side, we may query also internal nodes as well. Each query reveals a certain type of information. For example, in the left-hand side, given 3 nodes, the query can tell us which pair has the lowest common ancestor. And on the right-hand side, given 2 nodes, the query tells us is U an ancestor of E? And another thing to note is that we can query only leaves of a biological phylogenetic trees because apart from some exceptions, most of the species most of the previous species have been extinct, so we have only access to the leaves of the tree. On the other hand, we can query any nodes of a digital phylogenetic trees, as these objects may have been, archived. So the motivation for learning the tree and understanding the evolutionary process of the objects comes from the desire to better understand the evolutionary process of the objects. For example, learning and studying the biological evolutionary process can help us to, characterize and, categorize the fossil records, and also to see which relatives are, which species are close relatives. On the other hand, studying the way that how digital objects have been edited or transformed through the passage of time can be useful in computer security, or data protection, copyright disputes, and plagiarism detection. For example, studying the evolutionary process of a computer virus can provide us some information about its ancestry, about the characteristic of the attacker, and also about the ways that the future attacks may appear, and how do they look like, and where are they going to be appear. So in this work, we have 2 performance measures, and the first one is the total number of queries to issue to reconstruct the tree. And previous work just consider this performance measure because they were mostly focused on sequential algorithms. And another performance measure is the round complexity, or the total number of rounds of queries that is required for reconstructing the tree. And in many applications, the queries can be done in batches. For example, nothing is preventing biologists from conducting their experiments in parallel. So the first problem is that given a set of leaves of a biological phylogenetic tree, we want to learn the tree using 3-node closure query, or also known as relative distance query. So the query works like this. Given 3 leaves, A, B, and C, it returns the pair with the lowest common ancestor, which is in this case A and B, as you can see. So the previous work for this problem have been focused on sequentially reconstruct the biological phylogenetic trees, and the first one is by Cannon et al. They provide the quasi-linear number of queries, and their approach was an incremental approach, and it was reminiscent of insertion sort. The second one is by Imamjomezadeh and Campbell, and it also has a quasi-linear number of queries, but it was designed for another context, also known as hierarchical clustering, where the goal is to provide a hierarchical grouping structure of the objects according to their similarity. So the algorithm works like this. We pick 2 random leaves, A and B, and we perform query closure for every other leaf, C, and the pair A and B, and to split the tree into 3 sets, A, B, and R. The set A is the set of nodes where the answer of closure A, B, and C is AC, and the set B is the set of nodes where the answer of closure ABC is BC, and the set R is the set of nodes where the answer of closure ABC is AB. So we split the tree into 3 sets, and we just recursively build the tree for each section. After that, we just need to merge the tree, and as it's obvious that the lowest common ancestor of A and B should be the parent of the rooted tree of the set of A, and it also needs to be the parent of root of T of B, right? And it is worth it to note and to see that each internal node recursively is labeled with a pair of nodes, with a pair of leaves, one from the left subtree and one from the right subtree. So in order to just complete the proof, we just need to find out what is the parent of the node labeled as AB. In order to do that, we just need to find the first point where the node A is closer to one of these C and D, but is not closer to E and F than the pair itself. So we link the node AB to an edge from CD to EF, such that the closer response from ACD is not CD, and the closer response from A, E, and F is basically E and F. And in order to do that, we just need to query closer of A, and every pair of leaves that represent an internal node. So we need just O of n queries in one round to merge these three series. So steps 2 and 5 can be done in parallel, and they take of n queries and one round each of them. And obviously we can recursively build the trees for each of the section in parallel. And for this analysis, we have that with constant probability, a round of algorithm 1 decreases the problem size of any recursive call by a constant factor. So we can reconstruct the rooted binary tree using quasi-linear number of queries and of log of n rounds with high probability. And the high probability analysis can be achieved by applying a Chernoff bound on the sum of the independent geometric random variables, and the fact that each iteration is taking O of n queries and O of one rounds. So we also have done some experiments, and the first experiment is using the tree-based data collection, and we compared our algorithm with the ones by Cannon et al. And the one by Imam Jomezadeh and Kempe. While we have got significant parallel speed up, we maintained almost similar total queries as compared to these two algorithms. And we also have conducted our experiments for random synthetic data that we have generated through the proofer sequence. And using random proofer sequence, we generated random tree, and we also apply our algorithm on the random tree as well, and we got the similar results. The second problem that I want to talk about is related to the digital phylogenetic tree, and also some biological phylogenetic trees, such as the viruses, which we have access to all their ancestors as well. So in this problem, we are given a set of nodes of a digital phylogenetic tree of maximum degree D, and we want to find the tree using path queries in parallel. Each path query or ancestor query works like this. Given two nodes U and V, it finds if U is an ancestor of V, or in the other words, if U has a path from if U has a path to V. So the previous work was by Wang and Honorio. They provided an algorithm which was a randomized algorithm, and it holds in expectation, and the total number of queries was of n log square root of log square of n, and they also provided a lower one saying that any randomized algorithm requires omega of n log of n queries. So in order to reconstruct the tree in this problem, we find the root of the tree, and for any non-root node of the tree, we find the parent of that node. So finding the root is not hard, but it requires O of n queries and O of log of n rounds to deterministically find it. So the algorithm works like this. We take an arbitrary vertex field, and then we find the ancestor set of V using pass of x to the v for all other x v in parallel, and after finding the ancestor set y of v, as we know that this ancestor set forms a total order, we can just apply any comparison-based maximum finding in parallel to find the root. So using acceleration cascades, we can find the root of the tree deterministically in O of n queries and O of log of n rounds. So another key idea in our algorithm is that the context of even edge separator. We say that an even edge edge is an even edge separator if after removing E, the both resulting subtrees are as big as at most a d-1/d factor of the original size of the tree. Remember that d is the maximum degree of the tree. So we know that every degree d3 has an even edge separator. It might not be unique, but it has an even edge separator. And the thing is, if we find an even edge separator, then we can build the tree recursively and probably very efficiently. Another thing to note is that if you take a random vertex from the tree, then with probability at least 1/d, the path from root to that node contains an even edge separator on it. And the proof is very simple. Just consider that xy is an even edge separator. Then if we pick v from the blue subset, then any path from root r to that node contains the edge xy, and as we know that each of these two subtrees have the size of at most d-1/d factor of t, then each of them should be also at least 1/d factor of the original size of the tree. So picking a vertex from the blue vertices just guarantees that we have an even edge separator on the path from root to that vertex. So if you pick a vertex uniformly at random, then with probability at least 1/d, there is an even edge separator on the path from root to that vertex. But the thing is, finding an even edge separator may be too hard because it may require finding the exact value of the number of descendants. Instead, we find a near edge separator. We say that an edge is a near edge separator if after removing E, the both resulting subtrees are at most as big as a factor of d plus 1/d plus 2 of the original size of t. So this is a more relaxed version of the separator, but it can still be efficient for us, and we just don't need to find the exact value of the number of descendants, and we can do sampling instead. So the algorithm works like this. We pick a random vertex v from t. We find ancestor set for v, similar to finding the root as I earlier mentioned. And then we check if there is a near edge separator on the path from root to that vertex. If there is not, we just repeat the step 1. If so, we just cut the tree using that edge separator, and the fact that a node is in the blue subtree if and only if the pass query from the node y to that node is 1. And after cutting these two trees, we can just recursively build the tree T1 and T2 and find all of the edges of the tree. In order to find the separator, just consider the path from root to that vertex. If the path was very huge and it was at least n over log of n, omega of n over log of n, we just take a sample s of roughly square root of n elements of y, and then we estimate the number of descendants for each of these sample nodes using a small sample of logarithmic size of size k in parallel. Then, if all of the estimates are greater than k times d over d plus 1, we guess that all of these nodes on the path have too many descendants to be a near edge separator. If all of the estimates were less than k over d plus 1, we guess that these the nodes on this path have too few descendants to be and to include an near edge separator. And note that we also added the R and V to the sample nodes that we are doing the sample, and our sample always include the two ends of the path. And if one of the estimates were somewhere between k over d plus 1 and kd over d plus 1, we just verify that by finding the exact value of the number of descendants. And if it was even a near edge separator, we just return it. If not, we go to the next step and we sort the sample in parallel in O of 1 round and O of at most n queries. And we pass the parse that we think it includes an even edge separator to the next phase or next step, step 2. And in step 2, we expect the path to be small enough such that we can estimate the number of descendants of each of the nodes using a logarithmic sample in parallel. And if just one of the estimates are at least k over d plus 1 and at most kd over d plus 1, we just verify that. And if the verification is successful, we just find the parent of S. In order to find the parent of a node, and in order for this algorithm to work efficiently, we need to find the parent of a node X in O of n queries and O of 1 rounds with high probability. In order to do that, our algorithm works like this. Until the size of the path of y is at most a constant factor of a square root of n, we take a random sample of roughly a square root of n elements of y, and we sort all of the elements of this S, and we just find all of the nodes which are smaller than x1, and we replace y with this new y, And we continue this loop until the size of y is at most of a square root of n. After that, we can just sort all of the elements of y in parallel and just take the minimum. So we expect that with high probability, we have at most 2 iterations. So we can find the parent of each node with O of n queries and O of 1 runs with high probability. And for the analysis, we can prove that with constant probability, any call to a split separator finder finds the separator using O of n queries and O of 1 runs. We can reconstruct the degree D tree using O of n log of n past queries and O of log of n runs with high probability. And our query complexity is dominated by 2 calls to the recursive to the two recursive calls and also of n side work, and our run complexity is the maximum of these 2 calls and also plus O of 1. So Q of n will be in O of n log of n and R of n is in O of log of n. In order to provide the high probability analysis, we just need to apply Chernoff bond on the sum of their independent geometric random variables with the probability of 1/2D, and the fact that we can model the recursion tree of the algorithm with a tree of height of log of n in the basis of b plus 2 over b plus 1. So we also have a lower bound saying that any algorithm to reconstruct the degree tree, it requires omega of n log of n plus nd past queries, and it works for a worst case of a deterministic algorithm and also expected value of a randomized algorithm. We have also conducted some experiments, and just like the previous part, we applied our experiments for the synthetic data where we generated our trees from preferred sequence, and this C2 just monitors the size of the sample size. If you remember, the size of the sample size was C2 times log of n, so this just monitors the size of the sample size, and we have implemented our algorithm with different constant parameters, and we compare our algorithm with the one by Wang and Hanario. And while we have achieved a significant parallel speedup, we also improved the sequential work by the algorithm as compared to the algorithm by them. And we also have applied our algorithm for the trees for the real data from tree base, and we got the similar results. We got significant parallel speedup while also improving the total query complexity as compared to the algorithm. Thank you for your attention, and I would be looking forward to take your questions. Thank you.